Hey, good morning, guys, or at least it's morning for me. I don't know what it is for you. Today we're going to talk a little bit about pressure. You can pause here if you want to read my cheesy pressure cartoons. So the idea of pressure, why does being pinched hurt more than if somebody grabs your skin? Why does somebody hurt more if you have to if you get pinched? It's because when you pinch, you create more pressure because you're concentrating that force in a smaller area, and that generates more pressure. Um, so the equation for pressure is the force applied divided by the area. Hey, I'm doing it. Um, so the force applied and divided by the area over which that force is applied. If you concentrate, if you make the area small, then you're going to increase the pressure over here. So the equation is P equals F over A, where F is force and A is area. Force is measured in newtons, and area is measured in meters squared. So when you take newtons divided by meters squared, you get a newton per meter squared, which is abbreviated as a Pascal or a PA, named after Blaise Pascal over here. So I don't have a good way of working problems on the board because, well, I don't really have a board that I can use. Well, I do, but I can't record it. So so anyway, you'll just have to bear with me here. So what is the pressure created by 50 newtons of force? So that's our F. If we concentrate that force of the area of our fingertips as in a pinch, and versus if we look at the area concentrated over the area of a hand, which would be 0.016 meters squared approximately. If you take pressure equals force over area, so for the pinch, 50 divided by 0.0002, you get 25,000 pascals, newtons per meter squared, or pascals, 25,000. If you take that same force and you spread it out over an area of 0.16, you get a little over 3,000 pascals. So the point being is that you generate a lot more pressure when you concentrate that force over a smaller area. Here's another problem. You have to try to work this on your own. I'm just going to go over it. So you've got 101,300 pascals or newtons per meter squared of atmospheric pressure. That's the air pressure that's on you right now, just due to the atmosphere being submerged in a pool of air, so to speak. And an average person has an area of 1.67 meters squared, at least somewhere around my size. What is the force on me? Well, using the equation P equals F over A, P here, this is our 101,300, equals our F, okay, divided by A, our area. So you set it up as 101,300 equals F divided by 1.67. Solving that for F, you multiply the pressure times the area, and you would get 169,000 newtons of force, or approximately 17,000 kilograms of mass. The weight of that mass is on you right now, which is an incredible amount of force. Uh, so why don't we like shrink to nothing? Well, if we go back to our discussion of solids, liquids, and gases, solids don't compress very much because the atoms are pretty close together already. When you squeeze on them, they don't really compress much in size. This is where I would typically do a bed of nails demo, where I would lay down on a bed of nails, and the reason that being that I don't get impaled by my nails is that there's quite a few nails, and we're able to spread out that pressure. Instead of one nail, if you were to lay down on a bed of nail, that would definitely be a different outcome than a bed of nails, because again, you're spreading out that force over the area of 200 nails, but you don't get to see it because we're not at school. Um, so what would happen to the pressure under this block if I stack another block on top of it? Well, the pressure here is going to increase because I wonder if I can move this, yeah, because the force is going to increase on it. So the weight that this surface is supporting just doubles. The pressure would double. So twice the force, twice the pressure underneath here. Um, Now, what would happen to the pressure if I stacked another block alongside of it? What would happen to the pressure under this one? Okay. Well, certainly the pressure isn't going to change at all underneath this block because I haven't affected it anyway. But the other way to look at it is, well, I do have twice the weight, twice the force, but I also have twice the area. So the pressure is going to stay the same. Is going to be identical under both of these. It'll be the same as it was before. So let's see. Okay, so under here, there's a certain amount of pressure. Under this one, there's twice the pressure because it's supporting 2 blocks. Okay, and under this block at the bottom here, it's 3 times the pressure of this one because it's supporting the weight of three cubes of concrete or whatever those are. Now, if I have 2 identical blocks, one is laying down and the other one is standing up, okay, which one is going to have the greater pressure? Okay. Well, they both have the same weight, so the force is the same. But if we look at the area of contact, this one has a larger area of contact and this one has a smaller area of contact. So which one is going to have the greater pressure? Well, the one that's got that force concentrated on the smaller area of contact. So this one, because it has less area, is going to have greater pressure. There was a submarine that went 6.8 miles. Now they've gone deeper than that, I'm sure now. But there was a submarine that went in the 50s here, 6.8 miles underneath the surface of the ocean, and there was 28,810 pounds of psi, pounds per square inch. So 2,800 pounds of force on every teeny square inch of that craft. It was filled with this buoyancy compartment was filled with gasoline, so that as opposed to air, because the air would have compressed and this would have collapsed. And this is where the people were. So when you're under the surface of a liquid or a fluid, make that general, there's a certain amount of pressure on you. And it works kind of the same way as what we were looking at before. We had a container of water here. The bottom of this container is supporting the weight of this fluid. So there's a certain amount of pressure at the bottom of that. So the weight of the water divided by the area of the contact of the surface or the bottom. Okay. Now, if I compare the pressure here versus here, okay, well, the pressure here is going to be twice as much as the pressure down here because it's got twice the weight on it. Okay, so 2 times the force over the same area. So it's going to have twice the pressure. Similar to the blocks of concrete, at the bottom, if I have 2 stacks of water per se, I'm going to have twice the pressure at twice the depth. Okay, just like 2 stacks of concrete. If we look at a small container of water versus a large container of water, if we look at the pressure at the bottom of this container and pressure at the bottom of this container, which one is going to have more pressure? Well, it's going to be the same because this one may have twice the water, but it also has twice the area of contact. So the pressure at the bottom of these tanks is going to be identical, similar to our scenario here, where we just stacked one concrete block next to the other one. So the pressure underneath these is the same as the pressure underneath those, or underneath that one. So one of the things that you want to take away from this is if we're looking at the pressure in a fluid, or a liquid or a gas like water, it doesn't depend on how much liquid there is. It only depends on how much there is above you or the depth you are in the fluid. Okay. So now if I compare, I have 3 containers of water, and we want to see which one has the greatest pressure on them. Well, we know that these 2 have the same amount of pressure at the bottom of them, or even if you're just submerged in them, you would feel that pressure. So let's just compare these 2 then. This one is going to have twice the pressure at the bottom of it because it has twice the weight of the water on top of it. Okay. So again, thinking back to our blocks of concrete, these 2, the left and the very right one, are the same. But this one has twice the pressure because it has twice the weight that it's being supported. So let's get to an equation here, and I'm not going to spend too much time going through the derivation of this. You can slow this down if you're interested. So pressure equals force over area, where the force is the weight of the fluid. Weight is equal to mass times gravity, so m times g divided by area, so m times g. Density is equal to mass over volume, so therefore mass, I'm sure you're riveted by this derivation, is equal to volume times density. Okay, mass is equal to volume times density. Let's substitute that in here. Okay, and then volume is equal to base times height. Okay, or which base is the area. So if we substitute that in, okay, we see that something cancels out, and that's the area. So the area doesn't matter. When we're talking about the pressure inside a fluid or due to a fluid, it doesn't. We don't really worry about the area. All that really matters is the density of the fluid, gravity, which is always 9.8, times the height, where the height is equal to the depth of the fluid. So that's really all that matters. These are the three components: the density of the fluid, gravity, which will pretty much always be on planet Earth, so it'll always be 9.8. And then number 3 is your depth in the fluid, which is usually really referred to as the height. So what does not matter is the total amount of fluid in the container. And I have water here, but it really means fluid in general. Could be alcohol, could be mercury, could be air. The shape of the container doesn't matter, and the area of the container doesn't matter. It really just matters your height in the fluid. So let's skip through some of this. So if we look at these two containers, I've got red dots marking a location. The pressure at both of these is the same. Even though this one has more liquid below it and more liquid total, it doesn't matter because these would be the same height, the same depth in the fluid. So the pressure at these red points are the same. Now, the pressure down here would be greater than pressure here, okay? Pressure down here would be greater than the pressure here, okay, because it's deeper in the fluid, but these two red dots are the same. Now, if I compare these now, okay, which one of these is going to have the greater pressure on? Well, it's still the same because they still have the same amount of fluid above them. That's what really matters, not how much fluid is below them or total. So if I were to ask you a question like this, so here we've got two containers. We've got a tall, skinny container that does not have a lot of liquid in it, and we've got a much wider, shallower container that has quite a bit more water in it. The question is, which of these red dots would feel more pressure? Well, the answer is it would still be this tall, skinny one, even though it has less water. It has a greater amount of depth in the fluid. So even though this has less water in it, this would actually have a greater amount of pressure on it. This would normally where I do a demo, but it's not that great of a demo, so you're not missing out on that much. So let's say I want to look at compare the pressure at the bottom of these containers here. I've got one filled with water and one filled with mercury, which is going to have the greater pressure at the bottom of it. Well, if you could even sink in mercury, which would be challenging, the pressure is going to be greater at the bottom of the mercury because, again, pressure is equal to depth times gravity times density. So if my density is greater and my gravity and depth are the same, then the pressure here is going to be greater. Number 6, what is the pressure 3 meters under the surface of a pool of water? The density of water is 1,000 kilograms per meter cubed. I need to make a point here. If you're using that equation, pressure equals density times gravity times height. The density has to be in kilograms per meter cubed. That is important. I should have mentioned that before. So to figure out the density, it would be density, to figure out the pressure, it would be density, so 1,000 times 9.8 times 3. And if you're working this at home, that would be 29,400. Now, what do we measure pressure in? Well, either newtons per meter squared or pascals. Number 7, what is the pressure 3 meters underneath the pool of a gasoline if the total depth of the pool is 6 meters? Okay, the density of gasoline is 680. It's less dense than water, which is why it floats on water. Well, again, pressure is equal to density times gravity times height. So the density is 680, gravity is 9.8. And then we've got two depth measurements here, 3 and 6. Well, I threw in that 6 just to mess with your heads. If we're looking at it 3 meters underneath the surface, that's the depth that we're going to use. We don't use the total depth of the pool. So that would be times 3. That would be 19,992 pascals or newtons squared. And so the density or the pressure underneath the water is greater than at the same depth under a pool of gasoline because water is more dense. So if we were taking a test, you would probably see a test question along these lines, which show these different people in different containers of water. And the question would be, who feels the greater water pressure? Well, all 4 of these people would feel the same water pressure because they're in the same fluid, which is water. They're the same depth from the surface, and gravity is the same. So this is showing that the shape doesn't matter. This is showing, again, shape doesn't matter, and the total amount of water doesn't matter. Okay, and this is again showing it doesn't matter how much water is below you or the total amount of water there is. Pressure just depends on the height, the depth of the fluid that you're in. So if I were to show you a similar picture, I have a tube of water, two glass things of water connected by, I guess, a glass channel here. And I would ask you which one of these points would feel more water pressure, the one underneath the skinnier tube or the one underneath the fatter tube. The answer would be the same. Okay, they would feel the same pressure because they're the same depth underneath the fluid. So if I had a little piston here or whatever, that piston wouldn't move either way because the pressure is the same on either side of it. And this is just another way of saying that water seeks its own level. Water will come to the same level in a if 2 containers are connected, which is why they actually use what's called a water level. If you're trying to make sure 2 things are the same elevation from a pretty good distance, you just use a tube of water, and you just make the water level the same as on both of those, and it works. I've used it before. So these are different containers showing that the water seeks its own level. Now, if you look closely, you'll actually see that the skinny tubes are just a little bit higher than the wider tube. That is not due to a pressure difference. That's due to something called capillary action, and you'll learn more about that in chemistry. But for the most part, the levels are the same. So if I were to ask you, if I were to remove these plugs, and in the instant that they were removed, which water would be shooting out more quickly? Just at the instant, not at like a second later. So the answer is that the water would shoot out identical because they would have the same pressure on both the openings. So this is supposed to be a cork. I probably didn't explain that very well. So the water would shoot out the same because the pressure on them is the same the instant that it's pulled. Which way are dams shaped? Okay, are they normally this vertical block or are they normally this triangular shape, which is normally done? Well, normally it's the triangular shape. Why would it need to be thicker at the bottom than at the top? Well, that's because as you go down the water level, the water pressure gets greater and greater as you get deeper and deeper. So that way you've got more concrete here to resist that pressure. Okay, and pretty much where I'm going to end. If you ever notice that when you drive down a hill, your ears pop, that's because you feel some pressure on your ears. That's because when you're driving up and down, okay, well, right now we're submerged in a pool of air. It doesn't seem like we're submerged in a pool of air, but we are pretty deep down in a pool of air. When you go down a hill, you're going deeper into that pool of air. Just like if you were to go deeper into a pool of water, you would feel that pressure on your ears. And when you drive down a hill, you're going deeper into a pool of air, and the pressure on your ears increases, and you have to swallow to make it equilibrate again. And that is where we're going to end. So hopefully that wasn't too painful. Talk to you guys again later.